By the way, is anybody going for help for this class in the Math Study Center?
I tried, but there's no stats.
How's it going over there? Are you getting decent help, or?
There's some people that are really good. You have to go like early in the morning before class. If you go like after, it's like impossible.
So they supposedly have coverage all day long, but I want to be really honest about this. It's really difficult as a tutor to take one course in statistics and then be able to fully tutor it. Does that make sense? So it's sort of like we don't really offer anything here that goes beyond Stats 1. So it is, we do require them to do some online testing to make sure that they're up to date once a year. So that supposedly they're up on the concept. But just keep in mind that if they're on the schedule to tutor statistics, they should be fully comfortable with it. And if you experience something that's less than what you expected, you should fill out an evaluation so that they can keep it effective. Does that make sense? So make sure to fill out an evaluation if you don't get good enough help. Okay. But that is one of the most difficult courses to kind of tutor because you only have one course under your belt at that point. So it's a little bit difficult to come at it. So please remember that on your formula sheet you can only have formulas. Right? No examples, no notes, no interesting shorthand of your own creation. Right? I love it. I had a student once that had these little weird symbols up in the corner, and I finally figured out it was a reference to the empirical rule or something. I like the creativity, but not in that case. So there's really no formulas for the box plot stuff, but does somebody remember what the box plot is created from? And there is sort of a formula we could write down if you want to, because it involves finding what?
1, 2, 3, and 4. Q1, 2, 3.
Yeah, and even something called Q0 if you wanted to, like the low, the high, and the quartiles in between. So if you wanted a formula for how to find percentiles, you can do that. So remember that the formula for the percentiles was, you could write down, let's see how I can put this. That's really the only formula you could do. I'm not sure if I would even want to write that down if I were you. But how do you find like P80? How do you find P80? Okay, that's formula sheet. This is not. How would you find P80? What's the 2 steps?
80 times.
Yeah, let's say that N is 120. I like it. So you take 80% of 120. So that'd be 0.8. That'd be like 80 over 100. That's the 80% times 120. Isn't that the percentage times the N divided by 100? That's where that formula comes from. But for me, that formula is freaky looking. I just remember 80% of the way in. So I take 80% of N.
96. Oh. And then you add 1.
So that's 96. And then what does it mean when you come out to a whole number?
You have to add 1.
You average 96 and 97. So that's step 1, step 2. Step 1 always tells you where the answer is. Step 2 says go find the answer. Right? So that's what that's required to be able to put a box plot together, is to figure out the low, Q1, Q2, Q3, and the high. So there is a problem like that on the practice test.
Can we put step 1, step 2 on the formula sheet?
No.
Can we put average?
No. Too many words. So that's all you could put down if you wanted to put something down. If I'm you, I might not put anything. The idea is easier than the formula makes it look. Okay. Got to go back and review how to find quartiles. So that's really all there is from that section. Then we had the whole chapter 4, which is not going to be on this test. There's no probability on this test. It had its own little thing. So then we get into chapter 5, which was all about the x and the p of x, right? And again, you're not allowed notes, but the first 3 letters here lead you in the direction of what this is also known as. Who remembers that? EXP. So what's mean also known as?
Expected value.
Cool. You guys look like, can't believe break's over. I got way too used to that.
Yeah.
I actually feel exactly the same way. And then however you want to write it, we'll write it like variance. But you got to be careful. Either you put the square root in for the standard deviation or you write it as variance. And this is the weird one that's not overly easy to explain, but that's that. So I do not want to see, again, formula sheet, not formula sheet. I don't want to see this on your formula sheet. I mean, that's obvious. Or at least I think it's obvious, and then I always get at least a few people doing this. No. You've got to know the procedure. Yeah.
Is it the summation of all of x
No.
squared p?
Yeah, if you want to make it really clear, you can do that. That is not in there. With me? That's why I only need, the next column would be x squared p of x. If I add those up, that number goes there. That's the sum of all of these. That's how that works.
Can I put the sigma inside the brackets on my formula sheet?
The sigma inside the brackets.
Yeah, so bracket sigma.
Yeah, it
x
looks
squared
better
p of
like
x
that.
bracket. Bracket
Oh,
sigma.
oh, like this.
Yeah.
Yeah.
Sure.
Yeah, that's better.
That's fine. It's just a little bit. I don't agree, but it's subjective. So this is a piece of. No. So that's the two formulas that deal with if they give it to you in x p of x form. Right, so I really would love if you guys get a lot of the overriding things. If they give me a list of data, we know how to find the mean and the standard deviation. If they give me data as numbers and percentages of those numbers, now I also know how to find the mean and the standard deviation. Right? And that's actually, I try to show you how these formulas are the same as the ones before, because what's on the bottom of the probability? N. And how do you find the mean? Add them up divided by n. So it's still the same formula, it's just written in a better way for the way they give me the data. Okay. So that was that. Right after probability distributions, we talked about a specific type of probability distribution, the binomial distribution, right? So we have formulas like the probability which we focused on after that last quiz. So I'm hoping those aren't overly horrible anymore. Okay, good. And then we have the two most beautiful little formulas ever for mean and standard deviation. What was the mean in this case?
NP.
NP. Kicks ass. And the standard deviation was? Yeah, you could put it as variance if you want to. You could put it as,
Square root.
so it's got to be square root of that for the standard deviation. You can put both of them down there. I don't care. It's formulas. You put down what makes most sense to you. Just don't forget to square root. Here or there.
I put down mu q.
Mu q. Oh.
What the? What?
No.
Oh.
I know what you mean. No. So how are we doing so far? Okay, cool. Let me think. It's always dangerous for me to go purely by memory. This is the one about probability. That's the one about binomial probability. Then we got into chapter 6, where the only real formula that we use there is this guy. To begin with. And then we get into the slight freakiness of central limit theorem. So what's the only thing that changes when you have to apply the central limit theorem? What's the only thing that really changes? And what's the central limit theorem?
Do the standard deviation divided by something.
Good. So one thing it says is that the new standard deviation for groups is the old one divided by a square root of the sample size. I still see that look in all your faces like, it's been a week, but I feel like it's been a year since I last did statistics. Central limit theorem was the one where, what's the magic number to make it come out normal? At least 30, yeah. So if I take a sample of at least 30, that means that my resulting picture of those averages will be normal enough. The mean will stay the same, because I don't care if I take one of you at a time or 5 of you at a time, the average age will be the same. That only makes sense. But the standard deviation will definitely get smaller. That also only makes sense. Every sample I take, their average should be closer to the real average than they would be one at a time. I'm probably not going to pick 20 of you and have an average age of 17. You with me? It'll probably be close to the real average age. That's why the standard deviation gets smaller. It's not why it gets smaller exactly like this, but let's just deal with the idea it does get smaller. How are we doing so far? Y'all very worried, I understand. So again, we'll do several examples of all this, whatever you guys want to take a look at. Oh, and then the one thing from chapter 7 that I'm going to ask you about is confidence intervals. Like that. So officially, I'm not even going to make chapter 7, any of chapter 7 homework due. If I'm you, I would do 7.3 homework. Because remember, I want to make sure you guys understand. We skipped 7.2 for the moment. Let me say that again. We skipped 7.2 for the moment. I always forget to change the order on my homework sheet because I strongly believe they should do 7.3 first because it builds off of something we already know. Yeah?
I'm sorry, so is no chapter 7 homework due?
I like it. No chapter 7 homework is due on the day of the test. I will have a problem that involves finding confidence intervals. So if I'm you, I might not finish that damn homework, but I'm going to start that damn homework. Yes. Because there are a few things in that section I haven't talked about yet, and I'm not going to really do anything new on review day. Does everybody understand?
Yeah.
Sweet. So anybody doing online homework, I got to go in. I can't remember if I I got to change the due date. So don't worry. Okay.
Online homework?
Yes, online homework. Anything else? Anybody have suggestions as to formulas I might have left out? Actually, there is one formula I left out.
Just Z-score.
The guy that goes along with this. This is if I know the X and I want to figure out the Z-score. What if I know the Z-score and want to figure out the X-score? It's just a rearrangement here, right?
Yeah.
So that's this guy. And this is the most... Why is that formula just so freaking awesome? Who remembers why that formula is nifty? It's a loophole in my command not to have any notes on here. Can you read this in English? I don't mean X equals, no. I mean, can you make a sentence out of this? How do I get to a data point? I start at the mean, and I go this many, that's a Z, right? This many standard deviations. If you think about it, that's exactly what a Z-score is. I'm going to ask you, you know I'm going to ask you this question. Here is a question on the test. What does a Z-score tell you? I'm going to have people that tell me it tells you the area. No, it doesn't. The area comes from where? Where do I find the area? The Z-score chart. That's what tells you the area. What does the Z-score tell you? How many standard deviations away from the mean to a data point? Cool. Sweet. So even less excuse to get that answer wrong. Okay. So any other formulas you think I might have missed yet?
So that x bar plus z sigma over root n, that equals x as well?
Remember, this gives you, so again,
What does that
over
equal?
here. We had this formula from before.
Confidence.
Remember that formula? And actually, we used that formula with a 2 in there specifically to find the min and max usual values. If I just put a z-score, that finds, if I go this far down and this far up, I'm going to catch so much data. In statistics, we don't normally know the mean, do we? We're finding out what the mean is. So I can't use the mean, I have to use x bar. Where does x bar come from? Where does x bar, what does x bar
Summation of
mean?
X over,
Not the formula, where does it come from?
you add up everything. And
Just-
it's
What's the difference between this and this?
One's
sample.
That's from a sample. So I must have taken a sample. So what else must change? Standard deviation. So that's why the formula it's exactly the same stupid formula. I don't know that, so I use this. That must have come from a sample, so I have to change the standard deviation. I'm really hopeful about that. That formula is actually, those kind of problems are kick-ass awesome because they're just plug and chug. The only thing you won't be given directly is the z-score. I'll tell you I want to be 99% confident. So you have to find the z-score that catches 99% of the data. Remember that? Not really. So we'll do a problem like that. Don't worry. We'll do several. I like that. You're all like, you actually said those words sometime. So we'll do some problems like that. Don't worry. Okay. So any other suggestions on formulas I might have left off? And again, I don't know if you guys realize, but on that insert that has the z-score chart, if you have an insert, if you have a new book, if you have a used book, it's probably been ripped out. There's also a formula sheet. I don't allow you to use that because it has too many words on it, but you can always double check and make sure you've written the formulas down correctly, right? Just don't trust your eyesight in my writing. So double check. Okay. So let's do this. Let's kind of work backwards. Let's maybe start with a couple of confidence interval examples, and then we'll work backwards. Everybody, is that this here? The first example I'll give you is very to the point. We'll do another example that will be more of a story example. We got to pick off the right values. Right. So the idea with a confidence interval was pretty simple actually. If I want to be 90% confident, then how far away from the mean do I want to go? I want to go far enough that I catch how much of the data? 90% of the data. If I catch 90% of the data, how confident am I that I caught a specific data value? 90% confident. That's the connection. So visually, I want to go up and down far enough so I catch 90%. So if I said I want to be 98%, you put a 0.98 in there. So how in the world do I find the z-scores that go with that actually tell me how many steps I have to take? How do I find the z-scores here?
Add them up.
Add what up?
Something has to do with that.
It's not a bad idea. It's math class. Just throw out an operation and see what's right. What is the z-score chart understand? Areas that are below a given z-value. Right? So for example, the z-value I always find myself is this one. Because how much is below it? 5%. 5%. There's 90 in here. There must be 10 out there. There must be 5 on that side. So if you look up 0.05 in the chart,
Plus or minus 4.645.
it's going to be one of those little asterisk dudes, right? If you look it up in the chart, you'll see if you follow it, you'll see it goes to this. Which means this one is same thing but positive on the other side. And again, that's exactly why in the formula there's a plus or minus. You want to give or take. Yeah.
What does that CI stand for?
Oh, confidence interval.
How do you do that?
put it up here. Sorry.
What is?
I'll show you two different
confidence
things.
interval
I'll show you.
Exactly.
Oh, yeah. Yes, yes, yes.
Yes.
It's an interval that contains the percentage of the data to make you that percentage confident that you caught the real mean.
That's 1.605, dude.
Okay, so let me say it again.
1.64.
So guys, tell me this. Is that X bar, is that the real mean of the population? I would put a lot of money on it not being so, right? Because where'd that come from? A sample. So if that is exactly the real mean, I would be blown away. I'm like, holy crap. I put a lot of money, and I don't bet very often because I know the freaking odds. I put a lot of money on that not being the real mean. So the whole purpose here, statistics, what does it try to do? It tries to take a sample to figure out something about an entire population. You with me? So here's the cool thing about this that I can't believe I haven't said until now. Whenever you see, of course we got a big election coming up. Whenever you see data about Romney, 48%, Obama, 44%, whatever. What do you see at the bottom of the screen? Because that would be the percentage of voters that they think is going to vote for those people. What do you always see at the bottom? Plus or minus 3, plus or minus 4. Where the hell is that coming from? Well, that's exactly coming from that part of the equation, plus or minus that error. So 7.2 actually deals with the percentages. And that formula gets a little freaky. That's why I didn't want to start there. But we're getting close to understanding where that plus or minus comes from. They didn't just say, I'm not really sure, just let's cover our asses, put plus or minus 5 in the bottom. They actually plugged in the data to see how big the error is. What they normally don't tell you is, how confident were they in the beginning? Was it a 90%? Was it 95? Was it 99? Gallup tells you. They almost always use 95%. Okay. So, there's my X bar. The real mean is somewhere. Most likely it's close to this. But to be 90% confident, I have to go up and down so much so I catch 90% of the data. Because then I'm 90% sure that I caught the real mean. How often would that not catch the real mean? 10% of the time. So I have a 10% chance of being wrong. And that, related to how it normally is pretty damn good. So that's why if you wanted to be more sure, you would make it 95%, 98%. You with me? So 95% is what they normally use. But in this case, I just want to use 90% just because. Okay. So here's my 31. We figured out now that that's how far I have to go. And now I'm finally going to come back to your question before I forget. If I was really smart, I would have turned this thing on earlier. So as
You gotta remember to look it up.
per usual method of operation, I've got to cover my work.
Because you're going back. You're trying to find this. It's gonna go from I screwed that.
Thanks.
Sorry, we didn't finish the problem.
All right, so exactly 0.05. So why am I not looking out here for 0.05?
You're trying to find a z-score from
It's
X.
not a z-score. I want to know the z-score. It's an area. Areas live in here. So the closest I can get to 0.05. Hey, this is 0.05 stuff. Those two are exactly the same distance away from 0.05, right?
Yeah.
So that's the one time that I make you, and in fact the book does mark that. There's other places where that happens, but these are special. because they're the ones most often used. So if you look at this and you follow this down, and actually we can see it right here, negative 1.64, negative 1.65, so it must be right in the middle, negative 1.645. How important is that negative sign? Not. Because the plus or minus is built into the equation. All I care about is the actual z-score. That's why at the bottom, they do have the negative 1.645, but don't freak out about that. The plus or minus is built in. Is that cool? So real quick, as long as I have this up here, what if I ask for a 92% confidence interval? What percentage is that? 4%, right? So 0.04. What's the closest I can get to 0.04?
You're looking at 1.75.
Yeah, there's the closest right there, right? 0.0401, and that z-score would be negative 1.7 something. Yeah, negative 1.75. You with me? So you would put, what would you put into the equation, x bar plus or minus z sigma? You would put 1.75 in for the z-score. And that, I want you to understand this, that's the only thing you are not directly given. You with me? Everything else you're given directly. It's crazy. So now here we know, I'm using this formula here. And the only thing, I know the x bar is 31, I know n is 42, I know sigma is 5.982. And now we figured out z for 90% is 1.645. Oh, and I forgot to show you. I'll turn that thing on again. In the bottom corner of the z-score chart is what I call the little baby chart. Do you see how 90% is on there?
Yeah.
And look at the z-score next to it. Will I always give you one that's on the baby chart? Obviously not. So you got to know the procedure. With me? But those are the three big ones. Those are the ones that are most often used in the real world. So now I hate teaching it plug and chug, but I've already told you the whole idea. So now it is plug and chug. X bar, give or take this many of the new standard deviations. So my suggestion is to calculate what first?
What's in the brackets?
Yeah, this here. Because that's known as the error. I love it. Because if you ever go to a fair, and to tell you honestly, I've never been to the freaking fair here. I've been on fairs on the East Coast, but not here. You can hate me as much as you want to. Oh, I miss my deep fat fried butter. But no. I don't know here if they have this, but they sometimes have like places where they guess your age or guess your weight. They don't have to guess your weight exactly, do they?
No.
They have to be within something. They have to be. You have to give them a little allowance. That's exactly kind of what that is. I'm giving myself an allowance within some, saying I'm 10% chance if I'm wrong, but I want to give myself a little room. And that's what this is. Give or take this. That's exactly what that is. So, can somebody help me out? What's that?
1.52.
Oh, okay. 1.52 roughly. And now you just have to add it, and you just have to subtract it to get your... So it's a lot like finding the max and min values, but it's not the same. It's a little more specific. It's the percentage that you're right is going to change, depending on what they tell you. So in this case, I want to be 90% sure that I'm right. 10% possibility I'm wrong. So then you get from 29.48 to 32.52.
Nice.
Okay.
So there's 90% chance that you catch them.
Exactly. And to be honest with you, I'm not going to require you on this test, but when we get deeper into the confidence interval section, you're going to have to write a little conclusion. And just to show you what that looks like, that's an interesting. We are 90% confident that the interval 29.48 to 32.52 years contains the true mean age. And again, I always try to take a step back from all the technical details here. You're just trying to come up with an interval from, I'm this sure that it's from here to here. You with me? And we do that a lot in real life. About how far away? It's somewhere between 20 and 25 miles. I'm not sure. So we do that for ourselves already. We give ourselves a little wiggle room. This is just making it a lot more formalized.
So could you say you're 90% confident that it's 31 plus or minus 1.52?
You could say that also, yeah. That it's within this interval. Cool. Yeah.
So this is just in case is a dude that's like 85, like way out there.
Well, we got to be careful because it's not related to any individual people. It's still talking about the average age of everybody.
Yeah, but if everybody's 20 and there's one dude that's like 150, right?
That's an extreme case. So if I take a sample, it's most likely that I won't get that extreme value and my data will be off. And that's that 10% chance that I'm wrong. So that's why I love statistics, and that's why other people don't trust it. Statistics is the most honest thing there is. It always says, dude, there's a chance I'm wrong. Because that's what real life is all about, like you just said. Right? There's only one person that's 85, everybody else is in their 20s. If I take a sample, I'm probably not going to catch the 85-year-old. Right? So whatever average I find is going to be wrong. It builds in that percent chance I'm wrong. Okay. So any questions about that? Let's do one more example. So this is going to be a little less direct.
I don't remember any of this.
Yeah.
Yeah.
Oh. So that is definitely, there are some problems in the homework that are like this. And of course there are some problems in the homework like that. And that's what leads people to think that there are word problems in statistics, but there aren't. There are just find the values, put them in the right place problems. This still is pretty direct, hopefully. I was really careful. There's one word I underlined to make sure that you understand that that is exactly what we need. If I knew a sample standard deviation, could I use it in this formula?
Yeah.
What's this formula require?
Standard deviation
Of a population. 7.4 gives us a little tweak to this formula if I only know a sample standard deviation. So that's coming up. That'll be after this test. So don't worry about that. So I've got to be real careful when I write this that you understand that this is a population standard deviation, so you know you can use this formula. Is that cool? Okay. So can you summarize for me from there what you know and what you need to know? What do we know for sure? All right, so the average was 6.49. 115 is N. Sigma is, careful now, 1.814. And I want the 97% confidence interval, so now I got to figure out what that z-score is. So take a second, or maybe several seconds, and figure that out. Call me over if you need help on that step, because that's going to be, you know I'm going to do that on the test. So you want to be able to do that. I would highly suggest, as always, to draw a picture of the situation. Kind of focuses your attention on what you need. Are you going to look up 0.03?
No.
Hell no, because that's the both tails, right? Let me just use that word for the first time. You'll see in the book they call these tails, the outside, the two tails. I just need this one. What's that?
0.015.
0.015. I love it. You see that? If there's 97% inside, there must be 3% outside, there must be 0.015, 1.5% on that side. I need that because the chart is kind of stupid. The chart only understands areas below a z-score, so I have to be careful how I treat the chart. It doesn't understand 3%. It only understands that 1.5% below that z-score. So what do you guys see for that?
2.9.
2.17, I love it. And it's exactly that. That doesn't happen very often, but it's exactly 0.015. Oh, sorry. How these things happen. So now do you have everything you need? Because that's the only thing you normally don't know. So go ahead and try to finish that out.
0.49.
Figure it out, don't say it. Yeah, that's good.
I guessed. I just wanted to get really close. It wasn't.
So just plugging stuff in here. X bar is 6.49. Give or take, the z-score we found, 2.17.
I can design.
So we think it's this. That's our best guess. And the book calls this a point estimate. That's our best guess because that's what we saw from our sample. So then we're going to say give or take this much just to cover our asses, right? So sigma was 1.814. N was 115. What did you guys get for the error here?
0.367069.
Do it again, sorry.
Dang, dude. 0.3671.
So 0.37?
Could you put 0.367?
Sure, yeah. I would say for this, you should be on the same level as this or more. Does that make sense? So if you go out 3 places here, that's good because it's more than 2. Does that make sense?
Yeah.
So in general, I'd say this should go maybe even 1 more out, but at least the same number of decimal places, at least. So now you just have to add and subtract that. Right, so we'd say it's between 6.12. So 6 point, this is when I wish I was ambidextrous. 6.86. So we are 97% confident that the true average number of hours of sleep, or the true mean, is between this many hours and this many hours. Notice how small the interval is. It's not very wide, is it? Why do you think, what's the key thing about this problem? Why do you think it's not very big?
Took 97%.
Large.
Now, I want to be careful. 97% would actually tell me I've got to go pretty far out. Because to catch 97%, I've got to go far out. So that actually makes me think it's going to be a big interval. Why is it small?
Because you have a large sample.
I have a relatively large sample. So mathematically, I'm dividing by square root of 150. That's pretty. I'm going to divide and make this error smaller. What else makes sense? For the first day, what makes a better sample? If you're not sure about something, what do? You take a bigger sample. So then you should be more sure about what you get. So we're not that uncertain about this because our sample was pretty big. Therefore, I don't expect this to be a very wide interval. We shouldn't be that far off. How are we doing? So I'd like to show you how the math does jive with what we actually knew coming into this class on the first day. We knew a bigger sample was better. There's math showing you that a bigger sample makes your error go down. That's nice to see. Okay, cool. All right, so what do you guys want to focus on now? Anything specific? You want to look at maybe NAV problem, just kind of keep going backwards?
Yeah.
A NAV problem, and then we'll do some other, we'll do like a central limit problem. Okay.
Yeah, well, we'll have one of those. I know it's not going to be 95%. It's going to be something weird.
Yeah. That guy ain't gonna make it easy. Let's see.
I forgot what NAV was. What's NAV? NAV? What's the acronym? Normal approximate binomial.
I'm trying to make it look pretty much what it's going to look like. And you can see the kind of thing on the practice test.
On the test, you're going to tell us when you use that nav.
Yep, I'll say use the nav. That is pretty damn nice. I'll make that point. Is the term NAB still used at all? NABs?
For what?
No, it used to mean Nabisco products, so you said also NABs.
Oreos?
No? Huh?
Oreos? We just call
Oreos?
them-
Whatever they make.
That's all they make anymore is Oreos.
That's a good name and everything, man.
It's easy to remember.
I guess not. Every year, more and more of my references go out the window.
It's just that
Alright, so let me catch up to you guys. What'd you get for N, P, and Q? N is obviously
180.
180. What's P?
0.480.
0.48. Real quick, I want you to notice, I can answer that P, I can figure out what P is without me saying I picked, what's probably that 7 of them or whatever. You don't get P by doing 7 divided by 180. You get P from directly me telling you. Just because I picked 7 people or 100 people, it shouldn't change the probability that any of them will do something. So Q, of course, would be 0.52. So what's the mean?
86.4.
I like it. So it's 180 times 0.48, 86.4. And the standard deviation would be
6.7.
6.7.
6.7.
Oh, 3.
Oh, 3.
Oh, 3.
Dude, huge difference.
You guys keep that?
Yeah.
Because of course I'm going off of trusting all of you. Okay, cool. Now before I can make a z-score, what is it when I say use the nav? What is the twist involved here? When I have central limit theorem, like the problem we're going to do in a minute, the twist is to change the standard deviation, right? And then all the other steps are the same. Here there's one thing that has to change, and what is that? No? That's the central limit theorem. What is wrong with me drawing this picture related to this problem? That picture is continuous. So can you have 28.73 Republicans voting for Romney?
No.
I'm not sure about the 0.73 person. It's kind of scary. Right? It's a person or it ain't. So if I have the mean, this is 86.4. I'm interested in 81, right? Here's 81. Who remembers
81 and a half.
what has to change to make it go from discrete people to continuous, what my z-scores need? What do I have to pretend is happening with the 81? What do I draw on the 81? I know it's been a week.
You have to draw the little box.
Yes. draw what it really is. It's a little box. And what's on the lower part of the box?
80.5.
80.5. And the upper is 81.5. So if I want at most 81, which way am I going to shade?
Down.
Going to shade down. I like it at most 81. Do I want to include 81?
Yes.
So if I start here, from this number, do I include 81?
No.
No, shit, so I better start there, from that number. So this question, the probability that at most 81 becomes that. That's the continuity correction. You're like, oh shit. So I like this idea that central limit theorem has one tweak. Standard deviation changes, standard deviation divided by square root of n, and then all the other stuff's the same. NAB has one tweak because it's an approximation for a binomial. Binomial is discrete. One person, two people, three people, but the z-score is continuous. Shit, so I better pretend that 81 is actually 80.5 to 81.5, because then it's continuous. Which means I just have to figure out what side of the box to go to. So now to make my z-score, my data point will be not 81, 81.5. Minus the mean, divided by the standard deviation.
What does that CC mean that you wrote above?
Continuity correction. Because it's correcting for the fact that it's not continuous. And when I first started to do this, I didn't say use the NAB. I just said, here's a problem. So you have to be able to identify the type of problem you're dealing with. So now at least I'm making it a little bit easier, but this is as far as I'm going to go. Easiness. So what do you guys get for that z-score?
-0.7.
Negative 0.731.
Cool. Is that what everyone else got? Negative 0.73? So what do you do now, once you got that number? You circle it and go to the next problem.
Yeah.
So be careful. I get that all the time. I get people that set it up beautifully and they do all this work and then they stop at the z-score. I'm like, shh. This question asks for a probability, not a location. The z-score tells me where I am. I got to now look up the probability, right? Two problems. It's a z-score and it's freaking negative. Probability can't be negative. So what do you get when you look up negative 0.73? 2327? So that means the probability x is at most 81 is 0.2327.
Would we get it wrong if we put Px is less than 81.5?
No, that's fine. But you do want to reference that was an internal adjustment to get the number. What question are you answering? This question.
The original.
Yeah. But if you put that, I'll understand. It's nothing major, but that's the question you're answering. To be totally correct, it should say approximately, but you know, if you don't put that, it's not a big deal. Yeah.
So if it's at most, you go up 0.5, and if it's at least, you would go down 0.5?
Now, don't do that to yourself, because
Draw the picture.
yeah, trust me. There are too many situations to remember, because it could be at most, at least, it could be more than, it could be less than. So if you want to memorize all the possible situations, feel free. But it takes 5 seconds to draw a little box and say, okay, start this way, so I include it. Because it totally depends on which way I'm shading, you know, if I'm going to include it or not. Yeah.
What I don't understand is, did you explain the why we chose 81.5 instead of 80.5?
Yes, I did. If you choose 80.5, you're going to shade down. Does that include 81? No. So that's why I chose the other side. 5 seconds of thought instead of memorizing and taking up valuable
So
neurons.
that's the whole NAB thing is making
Exactly. Making an adjustment to the actual number you're given to make it fit the z-score chart better.
so you're making a discrete fit.
Exactly. That's why it's called a continuity correction.
That's what you're supposed to
So
do.
how do you get NAP?
Normal approximation to the binomial distribution. So I just call it NAP. Normal
It says on the
approximation to
skin,
binomial.
though. We're doing at least 81. It's kind of gay.
Yeah, if you were doing at least 81, let's say, you're doing at least 81. Here's your box, 80.5, 81.5.
You shade the other way.
At least 81, which way are you going to shade up now, right? Do you want to include 81?
Yes.
Yeah.
Yes. At least 81. 81 is at least 81, right? So do you want to start here?
No.
Because you wouldn't include it. You want to start there. So if I said more than 81,
Then you would not. You start at 81.5.
We go above 81.
then you don't want to include it, so you would make that. You see what I mean? Don't try to memorize. Oh my God, you'll be like,
Draw the picture.
no, just draw it and take a look at it. Don't make it more than it is. It's not really that. Just do include it or no. Which side do you want to start on to make that happen? Cool. Real quick, this is how you would check this. Oops. We did talk about this a little bit, the C and the P. Do you have to know how to use this? No. Can you to check your work? Yes. Not to do your work? No. But if you put in here NPX, I don't know if you guys remember that. It's also on your little calculator Bible. So if you put in there binomial CDF, what was it? 180.48 up to 81, right? So that's what C does. C is cumulative. It goes from 0 up to the number you put in. So if you do that, say again, sorry? 257? And what did we think it was? That's damn close. It's not the same, that's why it's got the word approximation in it, but it should be pretty close. Now one little thing I forgot, to be honest, and I will put this on the test, this is like A part 2. Because I'll put it before I ask you to do this, I'll say check NP and NQ. Who remembers what that's all about? How do I know I can use a normal distribution here? What do I have to check NP and NQ to make sure they're both greater than 5. Yet another thing that cannot be on your formula sheet. You have to know it, right? NP was 86.4. NQ is going to be 93.6. Yeah. So they're both bigger than 5. So I got that a different way, but you could do N times Q to get that, right?
Right.
So remember that the basic idea was I've got to get the mean somewhere in the middle so it has room to go up and come back down. So if the mean is too small, if it's less than 5, there's not enough room for it to go up. It's going to start high and go low. That doesn't look normal. So that those two kind of put it in the center. You got room to go up and come down.
So if it's less than 5, then you just don't do the problem.
The what?
Yeah, if it's less than 5, you can't use the NAP.
And times 2.
So what do you think we're going to make sure?
I know how to do this. I just don't
greater
know
than
when to
5.
do it.
Should that just be step 1?
It's gonna only last 2 seconds.
No, because part A, you figure out NP anyway. So that's
Cheap ass Easter bunny.
all you need for that is NP.
Truly know it. I'm gonna have to watch the video like 10 times.
Yeah.
We've been on way too long. That's a problem. We're all gonna have any standard deviation. Like 12%.
Don't say that.
I do well on the quizzes, just not on the test because it's too much to remember. Then I gotta go to the jazz club.
All right, guys, we got a little bit of time left. You want to do? Let's do like a central limit theorem type problem. Everybody has this here?
You want to include that form that has this.
Yeah. Oh, perfect time.